There is a strange world whose atmosphere stretches deep and hot and turbulent. Layers of gas pressing down upon layers. No solid ground anywhere below to stop the descent into ever-increasing heat and pressure. Somewhere within this churning sky, something falls that has no equivalent anywhere in our own solar system. Something that would seem impossible if we had not detected its signature across the light years separating this world from our own. The first time I encountered the details of this planet, the strangeness of it settled into my mind slowly, each fact more remarkable than the last, building a picture of a place unlike anything familiar. Within the atmosphere of HD 189733b, tiny particles of glass form high in the cooler upper layers and begin to fall through the surrounding gases. These particles are made of silicates, the same family of materials that form sand and quartz and ordinary window glass here on Earth, compounds built from silicon and oxygen atoms arranged in rigid structures. The particles condense from vapor when the temperature drops enough for these materials to solidify out of the surrounding atmosphere, much as water vapor condenses into droplets or ice crystals in the clouds of Earth. The glass forming in this alien atmosphere is not the result of manufacturing or any artificial process, but simply the natural consequence of chemistry operating at the temperatures and pressures found in this particular world's upper layers. When the atmosphere contains vaporized silicates, and when those vapors rise or circulate to regions cool enough for condensation, solid particles form spontaneously from the surrounding gas, crystals of glass precipitating out of the sky. The process is similar to how rain forms on Earth, where water vapor condenses when air cools, except the substance condensing here is glass rather than water. You are listening to The Drowsy Astronaut, and tonight we are exploring a world where glass rains from the sky and winds blow faster than anything we can compare to from Earth experience. If you enjoy these calm journeys through the cosmos, consider leaving a comment about where you are listening from tonight. Perhaps a like if you find this helpful for rest. The planet we explore tonight exists 64 light years away, and it has been there for billions of years, patient and indifferent to whether anyone ever noticed its strange weather. We have time to explore it slowly, letting the details settle in gently as the night continues. The particles of glass that form in the upper atmosphere are small, perhaps similar in size to fine dust or the particles of ash that drift from distant fires, tiny enough to remain suspended in the atmosphere for a while before gravity pulls them downward. These are not large chunks or shards, but microscopic grains, countless in number, drifting and falling through the alien sky, like the finest possible rain or the gentlest snow. The particles catch whatever light reaches this region of the atmosphere, glittering faintly as they drift through the surrounding gases. The composition of these particles connects them to familiar materials on Earth, where silicates form the bulk of rocks and sand, and the glass in windows and bottles. Silicon dioxide in crystalline or glassy form makes up much of the Earth's crust. The beach sand between your toes, the quartz crystals sometimes found in the ground. The glass rain of this distant world is chemically similar, built from silicon and oxygen, though it forms through atmospheric processes rather than geological ones. The formation of silicate particles requires temperatures that would seem impossibly hot by Earth standards, yet cool by the standards of this scorched world's deeper atmosphere. The upper atmosphere, where glass forms, might be roughly 1,000 degrees Celsius, which seems extreme until you consider that deeper layers are even hotter, too hot for silicates to condense. The glass forms in what passes for a cool region on this world, a place where temperatures merely melt most metals rather than vaporizing them. The particles drift downward after forming, pulled by gravity toward the deeper, hotter regions of the atmosphere, where they will eventually encounter temperatures high enough to vaporize them back into gas. This creates a cycle where silicates condense in the upper layers, fall toward the depths, evaporate in the heat, rise again as vapor, and condense once more when they reach cooler altitudes. The glass rain never reaches any ground because no ground exists on this giant planet, just atmosphere growing denser and hotter without end. The rain does not fall straight down as rain does on Earth. Though, and this is perhaps the strangest aspect of this already strange phenomenon, winds in the atmosphere of this world blow at speeds that defy easy comparison to anything in human experience, carrying the glass particles sideways as they fall. The particles drift downward through gravity, while simultaneously being swept horizontally by winds moving faster than any storm Earth has ever produced, creating a rain that travels sideways more than it travels down. The image of glass raining sideways through an alien sky presents one of the more remarkable pictures of planetary weather that astronomers have assembled from observations of worlds beyond our solar system. Nothing in our solar system produces conditions quite like this. No world we can visit or study up close demonstrates this particular combination of chemistry and meteorology. The glass rain of HD 189733b is unique among known worlds, though similar processes might occur on other hot giant planets we have not yet characterized. The detection of silicates in this planet's atmosphere came through careful analysis of light that had passed through the outer layers of the atmosphere during transits, when the planet crosses in front of its host star, as seen from Earth. Different substances absorb light at different wavelengths, leaving characteristic signatures in the spectrum that trained instruments and careful analysis can identify even across interstellar distances. The silicate signature told astronomers that glass-forming materials existed in the atmosphere in sufficient quantities to affect the light passing through. The blue color of this planet, which we will explore more thoroughly later, also connects to the silicate particles suspended in the atmosphere, scattering certain wavelengths of light more than others. The same particles that form the glass rain also give the planet its characteristic color, a blue similar in appearance to Earth, but arising from completely different causes and materials. The rain and the color are connected, both consequences of silicate chemistry operating in this unusual atmospheric environment. The particles falling through the atmosphere are too small to see individually, microscopic grains that would be invisible even if you could somehow position yourself within this hostile sky to observe them. Yet, in aggregate, they form hazes and clouds, collections of countless particles that affect how light travels through the atmosphere and contributes to the overall appearance of the world. The glass rain is both invisible at the particle level and visible at the atmospheric level, a matter of perspective and scale. The temperature at which silicates condense depends on pressure as well as heat, and the complex layered structure of this atmosphere creates regions where condensation can occur, even though the overall environment is extraordinarily hot. Higher altitudes mean lower pressure, which affects the temperature at which phase transitions happen, creating the possibility of solid particles forming in what would otherwise seem like impossibly hot conditions. The physics is the same as the physics governing condensation on Earth, just applied to different materials at different temperatures. The glass rain connects this world to the broader category of exotic precipitation found throughout the solar system and beyond, phenomena that challenge our Earth-centered intuitions about what rain can be. Saturn's moon Titan has rain made of liquid methane, falling from hydrocarbon clouds onto a frozen surface. Some gas giants may experience rain made of helium, dense droplets falling through hydrogen atmospheres. The glass rain of this world takes its place among these strange precipitations. The cycle of condensation and evaporation that drives the glass rain also moves energy through the atmosphere, transporting heat from deeper layers to higher ones as material circulates through the vertical extent of the atmospheric column. This energy transport affects the overall temperature structure of the atmosphere, influencing wind patterns and weather in ways that connect the rain to the broader atmospheric dynamics. The glass rain is not just a curiosity, but an integral part of how this atmosphere functions. The particles falling sideways through this alien sky have been falling for billions of years, the same processes operating since this planet settled into its current configuration, orbiting close to its host star. The rain was falling before Earth existed, before the sun ignited, before the solar system condensed from its parent cloud of gas and dust. The glass rain is ancient, ongoing, and indifferent to observation, a process that simply occurs because the conditions make it inevitable. The strangeness of glass rain becomes less strange when you consider that rain is simply condensation falling through an atmosphere, and condensation depends on what materials are present and what temperatures exist to allow phase transitions. On Earth, water is abundant and temperatures are right for water to condense, so we get water rain. On this world, silicates are present and temperatures are right for silicates to condense, so glass rain falls instead. The underlying physics is familiar, even if the specific conditions are not. The glass rain continues falling tonight, 64 light-years away, carried sideways by winds we will explore in the next stage of our journey through this remarkable atmosphere. The particles form and fall and evaporate and form again, a cycle that has continued for eons and will continue for eons more, regardless of whether any observer ever turns attention toward this small point of light in the constellation of the Little Fox. The rain simply falls, obeying physics, shaping the atmosphere, giving this world one of the most unusual weather patterns we have discovered among the thousands of planets now known beyond our solar system. The winds that carry the glass rain sideways across this alien atmosphere move at speeds that require careful attention to understand, velocities so extreme that comparison to Earth weather fails to convey the reality of what happens in this churning sky. Measurements indicate winds blowing at approximately 5,400 miles per hour, a figure that seems abstract until you try to place it in context against anything from human experience or Earth observation. These are not gentle breezes or even fierce storms, but something beyond the range of ordinary atmospheric phenomena. The fastest winds ever recorded on Earth occur in tornadoes, where spinning air can reach perhaps 300 miles per hour in the most extreme cases that have been measured directly. The winds on HD 189-733b blow roughly 18 times faster than the worst tornado winds, moving the atmosphere at velocities that make Earth's most violent storms seem almost calm by comparison. The scale of the difference challenges intuition about what atmospheric motion can be. At 5,400 miles per hour, the winds blow fast enough that an object caught in them would cross the continental United States in about 30 minutes, if it could somehow maintain that speed without being affected by any surface. The winds blow faster than commercial jets fly, faster than most rockets travel, faster than nearly anything in everyday experience, except perhaps bullets fired from certain weapons. The atmosphere moves at a speed that belongs more to engineering than to weather. These winds are supersonic by Earth standards, meaning they exceed the speed of sound in Earth's atmosphere at sea level, which is roughly 760 miles per hour, depending on temperature and conditions. Sound itself cannot keep up with these winds in an Earth-like context, though the speed of sound in the hot, dense atmosphere of this alien world is different and harder to characterize simply. The comparison to supersonic flight conveys something of the violence inherent in atmospheric motion at these velocities. The cause of these extreme winds relates to the fundamental structure of this world, particularly the fact that it always shows the same face toward its host star, locked into a configuration where one hemisphere experiences permanent day, while the other experiences permanent night. This arrangement creates an enormous temperature difference between the two sides of the planet, with the day side heated continuously by the nearby star, while the night side faces only the cold darkness of space. The winds blow because this temperature difference must somehow be equalized. Heat flows from hot regions to cold regions, and in an atmosphere, this flow takes the form of wind carrying warm air toward cooler areas where it can radiate energy into space. The greater the temperature difference, the faster the winds must blow to transport enough heat to reach equilibrium. And the temperature difference on this planet is enormous. Hundreds of degrees between the hottest and coolest regions. The extreme temperature gradient drives extreme winds, physics demanding that the atmosphere move fast enough to carry the necessary heat. The direction of the primary wind flow is from the day side toward the night side. Warm atmosphere streaming around the planet toward the cooler hemisphere in a circulation pattern that wraps around the entire world. This flow is not simple or uniform, but involves complex patterns of rising and falling air, zones where winds are faster or slower, jet streams and eddies and turbulent regions within the overall circulation. The atmosphere churns constantly, driven by the relentless input of heat from the nearby star. The winds carry everything with them as they blow, including the glass particles that form in the upper atmosphere and any other suspended materials or condensates that exist within the atmospheric column. The glass rain does not fall straight down because the horizontal wind speed is so much greater than the vertical fall speed of the tiny particles, sweeping them sideways far faster than gravity can pull them down. The rain falls at an angle that is nearly horizontal, more sideways than downward. The experience of being in such winds, if somehow you could survive the temperature and pressure and lack of breathable air, would be nothing like any wind experience available on Earth. Even hurricane winds, which can blow at over 150 miles per hour in the strongest storms, feel like gentle breezes compared to the atmospheric motion on this world. The force of wind increases with the square of its velocity. meaning winds blowing 18 times faster exert forces hundreds of times greater than Earth's worst storms. The sound of these winds is difficult to describe or even to predict accurately, since sound propagation depends on the properties of the medium through which it travels, and the hot, dense atmosphere of this planet differs greatly from Earth's air. Whether an observer could hear anything, or whether the wind speed itself exceeds the local sound speed and creates constant sonic phenomena throughout the atmosphere, remains uncertain from our distant observations. The world might be filled with sound or filled with strange silence, depending on physics we cannot fully characterize. The winds have been mapped, to some extent, through observations of how the atmosphere's properties vary across the disk of the planet, as seen during transits and other orbital phases. The hot spot on the planet, the warmest region of the atmosphere, is shifted from the point directly beneath the star, carried eastward by the winds that transport heat around the world. This shift tells astronomers about wind speed and direction, providing evidence for the extreme atmospheric motion, even though we cannot see the winds directly. The energy required to drive these winds ultimately comes from the star, whose radiation heats the dayside and creates the temperature difference that the atmosphere attempts to equalize through circulation. The planet receives intense radiation from its nearby host star, absorbing this energy on the dayside and distributing it through atmospheric motion to the night side, where it radiates back into space. The winds are part of the planet's thermal regulation system, preventing the day side from overheating and the night side from freezing. The circulation pattern that produces these winds may involve a single large jet stream wrapping around the planet's equatorial regions, carrying the bulk of the heat transport in a coherent flow that moves faster than the surrounding atmosphere. Alternatively, the circulation might be more complex, with multiple cells and countercurrents that together accomplish the heat transport through a more intricate dance of atmospheric motion. Theoretical models suggest different possibilities, and observations continue to refine our understanding. The winds affect everything about this planet's atmosphere, from the distribution of chemical species to the formation and transport of clouds to the overall temperature structure visible in our observations. Nothing in the atmosphere happens in isolation from the wind, which touches everything and shapes everything through its constant, powerful motion. The glass rain, the temperature patterns, the chemical distribution, all bear the imprint of the winds that carry them. The persistence of these winds over billions of years demonstrates the stability of the forcing mechanism, the unchanging geometry of a planet, locked facing its star and continuously heated on one side while dark on the other. As long as the planet remains in its current orbit and its star continues shining with similar intensity, the winds will continue blowing at similar speeds, transporting heat and carrying particles sideways through the alien sky. The winds are as permanent as the planet's orbital configuration. The glass rain falling sideways through these screaming winds creates a weather pattern found nowhere else that we know of. A combination of exotic precipitation and extreme atmospheric motion that defines this world's atmospheric character uniquely. Other planets have strange rain, and other planets have extreme winds, but the specific combination of glass particles swept sideways at thousands of miles per hour belongs to this particular world, and perhaps others like it, that we have not yet characterized in similar detail. The blue color of this planet, visible when astronomers measure the reflected light during certain portions of its orbit, connects to both the glass particles and the way light interacts with an atmosphere full of suspended materials in constant motion. The winds spread the particles throughout the atmosphere, maintaining the haze that gives the planet its characteristic appearance from afar. The blue color of HD 189733b marked a significant achievement when astronomers first determined it. The first time anyone had measured the visible color of a planet orbiting another star, a milestone in the growing effort to characterize worlds beyond our solar system. The planet appears deep blue, a shade reminiscent of Earth seen from space, though the similarity in color arises from completely different causes operating through similar physics. This world is blue, not because of water or sky, but because of glass. The measurement of this color required comparing the light from the star system when the planet was visible beside the star to the light when the planet was hidden behind the star during secondary eclipse. By carefully measuring how much light of different colors disappeared when the planet went behind its star, astronomers could determine how much light of each color the planet had been contributing to the total, revealing the spectrum of reflected light that defines the planet's color. The technique was delicate but effective. The blue color indicates that the planet reflects more blue light than red light, absorbing the longer wavelengths while scattering the shorter ones back toward distant observers. This selective scattering occurs because the particles in the atmosphere, including the silicate glass particles we discussed earlier, interact with different wavelengths of light differently, deflecting shorter wavelengths more effectively than longer ones. The same physics that makes Earth's sky blue operates here, though with different scattering particles. Rayleigh scattering is the name for this phenomenon, where small particles scatter short wavelength light more efficiently than long wavelength light, making blue light bounce around while red light passes through more directly. On Earth, molecules of nitrogen and oxygen scatter blue sunlight across the sky, which is why we see blue when we look up on a clear day. On this distant world, silicate particles and other atmospheric constituents scatter blue starlight preferentially, giving the planet its characteristic hue. The irony of a blue world so different from Earth emphasizes how misleading visual similarity can be when comparing planets across the cosmos. Earth is blue because its surface is mostly covered by liquid water oceans, and because its atmosphere scatters sunlight in the same direction as our eyes. This world is blue because its atmosphere contains particles that scatter light similarly, but it has no surface at all, no water, no oceans, nothing familiar except the color itself, viewed from extremely far away. The shade of blue is quite deep, sometimes compared to cobalt blue or the color of a sapphire, richer than the pale blue that Earth shows from space photographs. The exact hue depends on the specific properties of the scattering particles and the spectrum of light from the host star, which is slightly orange compared to our sun, and affects the overall color balance of reflected light. The planet appears as a deep blue point if we could somehow see it directly, which we cannot with current technology. The Hubble Space Telescope performed the measurement that determined this color, using its ability to observe at multiple wavelengths and its position above Earth's atmosphere to make the delicate measurements required. The observations took place in 2013, adding another piece to the growing portrait of this well-studied world that astronomers had been characterizing since its discovery 8 years earlier. Each observation added detail to our understanding. The significance of measuring an exoplanet's color extended beyond this single world to the broader effort of understanding what planets beyond our solar system actually look like, how they appear in visible light, what characteristics might distinguish different types of worlds. Color is one of the basic properties we notice about objects, and being able to determine the color of a planet orbiting another star represented a new capability in the young field of exoplanet science. The blue color connects to the silicate particles in the atmosphere through their size and composition, which determine how effectively they scatter different wavelengths of light. Particles similar in size to the wavelength of light scatter that light most efficiently, and the silicate particles in this atmosphere appear to be the right size to scatter blue light preferentially. The glass rain and the blue color are thus linked, both consequences of silicate presence in the atmospheric composition. The color also provides information about the overall atmospheric structure, since the scattering that produces the blue tint occurs at particular altitudes where the particles are present in sufficient numbers to affect the light passing through. If the atmosphere were clear at all altitudes, or if particles were present at different sizes or compositions, the color would be different. The blue tells us something about what exists in the atmosphere and where it exists within the atmospheric column. Earth's blue appearance from space includes both the atmospheric scattering that makes the sky blue and the reflection of blue light from the ocean surface, both contributing to the overall impression of a blue planet. The atmospheric component of Earth's blue is similar in physics to the blue of this distant world, but the oceanic component has no parallel on a gas giant with no surface at all. The comparison highlights both the similarities and differences between these blue worlds. Other hot giant planets might show different colors depending on their atmospheric composition and the properties of whatever particles or hazes they contain in their upper atmospheres. Some might appear gray or brown if they lack the right particles for selective scattering. Others might be reddish if different chemistry predominates. The blue of this particular world results from its particular chemistry, not from any universal property of hot giant planets as a class. The host star's color affects the overall appearance as well, since the light being scattered and reflected comes from the star rather than from the planet itself. An orange dwarf star emits relatively more red light and less blue light than our sun, which affects the total amount of blue light available to be scattered by the planet's atmosphere. The deep blue color indicates efficient blue scattering, even from a star that produces proportionally less blue light than our sun does. The color measurement represented a technical triumph, but also contributed to the scientific understanding of atmospheric physics, operating on worlds very different from anything in our solar system. No planet in our solar system combines the size, temperature, and composition needed to create these specific conditions, making this world a laboratory for studying processes that cannot be studied closer to home. The blue color is data as well as appearance. The atmosphere that produces this blue color is the same atmosphere we have been exploring throughout our journey, the same churning sky where glass rain falls sideways through supersonic winds, the same layered structure where temperature rises with depth toward eventually unbearable values. The color is just one aspect of this atmosphere, one property among many that observations have revealed, one piece of the puzzle that astronomers have been assembling since discovery. The blue world glows in the darkness of space, reflecting light from its nearby star Its color a consequence of physics, operating in conditions utterly unlike anything on Earth, yet producing a familiar result through unfamiliar means. The similarity of color and the dissimilarity of conditions together illustrate how diverse the universe of planets truly is. How many different ways exist to be a world? How much variety the cosmos contains beyond the single example we knew until recently. The temperature of this atmosphere, which drives so much of its behavior, including the condensation of glass and the extreme winds, rises as we consider the lower portions of the atmospheric column, approaching values that require new vocabulary to discuss adequately. The temperature of this world reaches values that exceed casual comprehension, degrees of heat that correspond to glowing metal and vaporized rock, conditions found in furnaces and forges on Earth, rather than in any natural environment we might encounter. The day side of the planet, permanently facing the nearby star, reaches temperatures of approximately 1200 degrees Celsius, hot enough to melt aluminum, hot enough to glow with visible light, hot enough that the very meaning of weather transforms into something alien. 1200 degrees Celsius corresponds to about 2200 degrees Fahrenheit. Temperatures normally associated with industrial processes rather than planetary atmospheres. Metal casting, glass blowing, and certain welding processes occur at these temperatures. Activities that require special equipment and careful safety procedures because the heat is so extreme. On this planet, such temperatures are simply the normal conditions in the atmosphere's upper layers, sustained continuously by radiation from the nearby star. The night side of the planet is cooler but still extraordinarily hot by any earthly standard, reaching temperatures of approximately 700 degrees Celsius, even though no direct starlight ever touches this hemisphere. Heat flows from the day side through the atmosphere, carried by the tremendous winds we discussed earlier, spreading warmth to the dark side of the world, even as it radiates energy into space. The night side glows with its own thermal radiation, visible in infrared light, even though it never sees the star. The temperature difference between the day side and night side amounts to roughly 500 degrees, an enormous gradient that drives the atmospheric circulation and maintains the extreme winds constantly blowing around the planet. This difference would be even greater without the atmospheric transport of heat, which moderates what could otherwise be even more extreme contrasts. The winds exist because of this temperature difference and simultaneously reduce it through their heat-carrying action. The atmosphere at these temperatures behaves differently than any atmosphere on Earth, with chemistry and physics operating in regimes that terrestrial experience does not prepare us for. Materials that are solid on Earth become liquid or gaseous at these temperatures. Chemistry proceeds at rates and through pathways not found in cooler environments. And the very concept of weather expands to include phenomena impossible under milder conditions. The glass rain itself is possible only because the temperature is hot enough to vaporize silicates in the lower atmosphere. The heat arrives continuously from the nearby star, whose radiation pours onto the day side without interruption, day after day, year after year, for billions of years since the planet settled into its current orbit. The star is slightly cooler than our sun, an orange dwarf rather than a yellow star. But the planet orbits so close that the radiation intensity is enormous, despite the slightly dimmer stellar output. The proximity more than compensates for the cooler stellar temperature. Different layers of the atmosphere have different temperatures, creating a complex vertical structure that affects where clouds form, where chemistry proceeds differently, and how energy moves through the atmospheric column. The upper atmosphere, where glass condenses, is cooler than the deeper layers, which is why condensation can occur at all, even though the entire atmosphere is extremely hot by Earth standards. The word cooler must be understood as relative rather than absolute in this context. The thermal radiation from the planet itself has been detected and measured by infrared telescopes, revealing the temperature of the outer atmospheric layers through the spectrum of emitted light. Hot objects glow, and this planet is hot enough to glow at wavelengths that space telescopes can observe, providing direct information about atmospheric temperature that confirms and extends other measurement techniques. The planet announces its temperature through its own thermal emission. The heat affects the chemistry of the atmosphere profoundly, driving reactions that would not occur at lower temperatures and preventing the existence of compounds that would be stable in cooler environments. Water vapor exists in this atmosphere despite the extreme heat, but in forms and amounts very different from what we know on Earth. Other molecules break apart or transform under the intense thermal energy, creating an atmospheric composition shaped by the temperature as much as by the available elements. The concept of a surface becomes meaningless at these temperatures, since the planet is a gas giant with no solid ground anywhere beneath its atmosphere. The temperature simply increases as you descend, the pressure building simultaneously, until conditions become too extreme to characterize with ordinary planetary science. There is no beach where you could feel this heat, no ground where a thermometer could rest, just atmosphere all the way down. The upper atmosphere, where temperature is coolest on this world, would still instantly destroy any probe or instrument designed for Earth conditions, the heat far exceeding the operational limits of conventional materials and electronics. Designing a spacecraft that could survive even briefly in this environment would require exotic materials and revolutionary engineering, and even then, the mission would likely be brief. We study this world from afar for very good reasons. The temperature creates the conditions necessary for the phenomena we have discussed, enabling the silicate chemistry that produces glass rain, driving the atmospheric circulation that creates supersonic winds, heating the gases that scatter light to produce the blue color visible from 64 light years away. The temperature is not just a property of this world, but a cause of its most distinctive features, the source of everything remarkable about its atmosphere. The heat also connects to the planet's position in its orbit, the tiny distance separating it from its host star, a proximity that we will explore more thoroughly soon. The temperature is high because the planet is close, and the planet is close because of its orbital history, a history that brought a giant planet from wherever it formed to its current position, nearly grazing the star it orbits. The temperature is a consequence of geometry and history. The thermal environment of this planet represents one extreme of the range found among known exoplanets, with other worlds orbiting cooler or more distant from their stars and experiencing correspondingly different atmospheric conditions. The diversity of planetary temperatures reflects the diversity of orbital configurations and stellar properties, each world experiencing conditions shaped by its particular circumstances. This planet sits near the hot end of that range. The furnace atmosphere continues deep below the layers we can observe, temperature and pressure climbing together toward values that physics can describe, but human experience cannot easily envision. The glass rain forms in the relative cool of the upper atmosphere, where temperatures merely melt most metals rather than vaporizing everything, and falls toward depths where even more extreme conditions prevail endlessly. The permanent alignment of one face toward the star results from a process called tidal locking, where the gravitational relationship between a planet and its star has reached a stable configuration after billions of years of gradual change. This world shows the same hemisphere toward its star at all times, rotating once on its axis in exactly the same period that it takes to complete one orbit, so that the two motions are synchronized perfectly. One side faces eternal day, while the other faces eternal night. The process that produces this locking involves the gravitational interaction between the star and any slight asymmetry in the planet's mass distribution, creating tidal bulges that dissipate rotational energy over time until rotation and orbit match. The same process has locked our moon to Earth, which is why we always see the same face of the moon from the ground, and it operates on any body close enough to another massive body for the gravitational effects to matter over long time scales. This planet orbits so close to its star that the tidal forces are enormous, much greater than the forces between Earth and Moon, making the locking process faster and more complete than in more distant configurations. The planet almost certainly became tidally locked early in its history, perhaps within the first billion years after it reached its current orbit, and has maintained this configuration ever since. The permanent day and permanent night have persisted for eons. The day side of the planet receives continuous radiation from the star, with no night to provide any respite from the heating, no rotation to spread the input energy across the full surface. The point on the atmosphere directly beneath the star, sometimes called the substellar point, receives the most intense radiation, with intensity decreasing toward the edges of the visible hemisphere as the angle of incoming light becomes more oblique. The heating is perpetual and uneven. The night side receives no direct radiation at all, facing only the cold darkness of space and whatever distant stars happen to lie in that direction, none of which provide significant energy compared to the nearby host star. Without the atmospheric circulation that carries heat from day to night, the night side would be extraordinarily cold, though still not as cold as you might expect, because even the attenuated heat transport of radiative processes would prevent truly extreme cooling. The terminator, the circle separating day from night, forms a permanent ring around the planet where the star sits forever on the horizon, neither rising nor setting, but hanging motionless at the edge of the visible sky, if you could somehow observe from within that zone. This terminator twilight zone experiences conditions intermediate between the blazing day side and the cooler night side, receiving indirect light and heat from various angles throughout the atmospheric column. The tidal lock-in creates the temperature difference that drives the extreme winds, since without the permanent day-night arrangement, there would be no permanent hot and cold hemispheres requiring thermal equilibration through atmospheric circulation. The winds we discussed earlier exist because of this locking, blowing from the permanent day toward the permanent night, in an endless attempt to balance what cannot be balanced as long as the star continues shining on only one side. The star appears enormous from the day side of this world, much larger in the sky than our sun appears from Earth, because the planet orbits so much closer to its star than we orbit to ours. The star would fill a significant portion of the sky if an observer could somehow withstand the conditions and look up, a blazing presence dominating the view in every way. From the night side, the star would never be visible at all, hidden forever by the bulk of the planet itself. The rotation period equals the orbital period, both measuring approximately 2.2 Earth days, meaning that a year on this world is also a day in the sense that one complete orbit equals one complete rotation. This quick orbit reflects the planet's close proximity to its star, where the gravitational influence is strong and orbital velocities are high. The planet races around its star in less time than a long weekend on Earth. The synchronization between rotation and orbit is not quite perfect in most tidally locked systems, with small oscillations or librations sometimes occurring around the equilibrium configuration. Whether this particular planet shows any such variations is difficult to determine from our distant observations. But the overall locked state is well established from the atmospheric properties that depend on the permanent day-night arrangement. The tidal forces that produced this locking also affect the planet's shape slightly, creating a bulge oriented toward the star that represents the equilibrium configuration of matter under the combined influence of self-gravity and the star's gravitational pull. This bulge is what locked into alignment with the star as the planet's rotation slowed, and it remains oriented toward the star as long as the locked state persists. The energy dissipated during the locking process came from the planet's original rotation, which was probably faster when the planet first arrived at its current orbit through whatever migration process brought it inward from its formation location. The rotation slowed over time as energy transferred from the rotating planet to the orbital configuration through tidal interactions until the present locked state was reached. Other tidally locked worlds exist throughout the galaxy, wherever planets orbit close enough to their stars for tidal forces to synchronize rotation and orbit within the age of the system. Many Earth-sized planets in the habitable zones of small red dwarf stars are thought to be tidally locked, creating permanent day and night hemispheres that might have interesting implications for potential habitability. The phenomenon is common, even if the specific circumstances of this world are extreme. The permanent configuration means that atmospheric patterns and weather phenomena persist indefinitely in the same regions, rather than moving around the planet as weather does on a rotating world like Earth. The hottest spot stays hot forever. The coolest spot stays cool forever, and the winds blow in the same directions for billions of years. The weather map of this world is static, even though the atmosphere churns constantly. The tidal locking connects to the planet's proximity to its star, which is the ultimate cause of most of the extreme conditions we have discussed throughout our exploration of this world. The proximity creates the heat, enables the locking, drives the winds, and explains why this planet differs so dramatically from anything in our own solar system. Understanding the orbit helps us understand everything else about this strange world. The orbit that brings this planet so close to its star measures only about 4.6 million kilometers at its average distance, a tiny fraction of the space that separates planets from stars in our own solar system. Mercury, the closest planet to our Sun, orbits at an average distance of about 58 million kilometers, more than 12 times farther from our star than this world orbits from its own. The proximity is extreme by any familiar standard. At 4.6 million kilometers, the planet takes only about 15 seconds to receive light that leaves the star's surface. compared to the 8 minutes that sunlight needs to reach Earth from the sun. The distance is so small that the gravitational interaction is intense. The radiation received is enormous, and the tidal forces are strong enough to lock the planet's rotation within a geologically brief period. Everything extreme about this world traces back to this close orbit. The star itself is slightly smaller and cooler than our Sun, an orange dwarf of a type astronomers call K-type, emitting perhaps 80% of the Sun's total light output and appearing distinctly orange rather than yellow-white to hypothetical eyes that could observe it directly. This dimmer star still heats the close-orbiting planet to extreme temperatures because proximity matters more than stellar brightness at such small distances. The inverse square law means that being 12 times closer makes radiation intensity more than 140 times greater. The star would appear immense from the planet's day side, filling perhaps 20 times the angular area that our Sun fills in Earth's sky. A glaring presence impossible to ignore if any observer existed to notice it. The solar disk we see from Earth appears about half a degree across, a modest circle, easily covered by an outstretched thumb, while this star from this planet's perspective would span many degrees, an overwhelming source of light and heat dominating the entire sky. The orbital period of 2.2 Earth days means this planet completes one full circuit around its star in less time than it takes Earth to rotate about 2.25 times. A year passing in what we would experience as a long weekend. The planet moves through its orbit at high velocity, covering the short orbital circumference quickly under the strong gravitational influence of the nearby star. The astronomical seasons of this world, if seasons had any meaning for a tidally locked planet with no axial tilt, would be measured in hours. The star is part of a binary system, orbited at great distance by a faint red dwarf companion that plays no significant role in the conditions experienced by the planet, but adds another astronomical element to this system. The red dwarf orbits about 200 astronomical units from the main star, far enough that it appears as little more than a bright point of light from the planet's perspective, if it could even be seen from the permanently illuminated or permanently dark hemispheres. The spectral type of the host star affects the overall color of the light illuminating the planet, shifting everything slightly toward orange and red compared to the illumination Earth receives from our yellow-white sun. The glass rain, the atmospheric scattering, all the optical phenomena we have discussed occur under illumination that differs subtly from what we experience, though the basic physics remains the same across stellar types. The star's magnetic activity also affects the planet, with stellar winds and occasional flares bombarding the close-orbiting world with charged particles and radiation beyond the visible light that provides most of the heating. The upper atmosphere may be slowly escaping into space, eroded by the intense radiation environment, though the planet is massive enough that this loss proceeds gradually over very long timescales. The star shapes its companion in multiple ways. The light travel time of 15 seconds represents such a small distance astronomically that this planet and its star form an intimately connected system, with gravitational and radiative interactions occurring essentially instantaneously by cosmic standards. Changes on the star affect the planet within seconds, and the planet's presence affects the star's behavior through gravitational interaction on similarly short timescales. The two objects are bound together closely. The orbit appears nearly circular, based on observations of how the planet's timing and position vary throughout its orbital cycle, suggesting that any original orbital eccentricity has been damped out by tidal interactions over the system's billions of years of existence. A circular orbit maintains constant distance from the star, contributing to the stable, unchanging conditions the planet experiences, rather than the varying conditions an eccentric orbit would produce. The orientation of the orbit allows the planet to transit its star, as seen from Earth, passing in front of the stellar disk twice per orbit and passing behind once per orbit, creating the viewing geometry that has made this world one of the best studied exoplanets known. This fortuitous alignment is what allowed the initial discovery and what continues to enable the detailed characterization that has revealed so much about conditions on this distant world. The orbital properties connect to the planet's history, suggesting a migration process that brought a giant planet from wherever it originally formed, likely in the cooler outer regions of the protoplanetary disk, where giant planets typically form, to its current position, nearly touching the star. This migration probably involved gravitational interactions with other objects, or with the disk material itself, slowly spiraling the planet inward until it reached its present configuration. The close orbit makes this world part of a class called hot Jupiters, giant planets orbiting very close to their stars, a category that was not expected to exist before the first examples were discovered in the 1990s. The discovery of hot Jupiters revolutionized our understanding of planetary system architecture, showing that the arrangement of our solar system is not universal, and that giant planets can end up in locations theory had not anticipated. The proximity that defines this world's character extends back to whatever events delivered it to its current orbit, processes that operated long ago, but whose consequences persist in the permanent day. The extreme heat, the supersonic winds, and the glass rain that falls sideways through this alien atmosphere today. The discovery of this world occurred in October of 2005, when French astronomers announced they had detected a planet transiting the star HD 189-733 using careful measurements of how the star's brightness changed when the planet passed in front of it. The detection added another entry to the growing catalogue of known exoplanets and set the stage for the detailed characterization that would make this one of the best understood worlds beyond our solar system. The transit method that revealed this planet works by monitoring a star's brightness continuously, watching for the slight dimming that occurs when a planet crosses between the star and the observer, blocking a small fraction of the starlight for the duration of the transit. The amount of dimming reveals the planet's size relative to the star, while the timing of repeated transits reveals the orbital period and allows calculation of the orbital distance. The technique is powerful, but requires the geometry to be favorable. Only a small fraction of planetary systems are oriented such that transits are visible from Earth's direction, since the orbit must be edge-on, or nearly so, for the planet to cross the visible stellar disk. This world happens to have such a favorable geometry, allowing transits to be observed every 2.2 days as the planet completes another circuit of its close orbit. The repeating pattern of dimming provided confidence that the signal was real. The star is relatively bright, as host stars of transiting planets go, visible through modest telescopes from dark sites and accessible to large professional telescopes for detailed spectroscopic study. This brightness made follow-up observations easier than they would be for planets around fainter stars, contributing to the intensive study that has characterized this world in the years since discovery. Bright host stars are valuable in exoplanet science. The discovery team was led by Francois Bouchy and included researchers from several institutions, following up on earlier radial velocity hints that a planet might orbit this star by searching for the transit signature that would confirm the detection and reveal additional information. The combination of radial velocity and transit observations provided both mass and radius measurements, allowing density to be calculated and confirming the planet's identity as a gas giant rather than a rocky world. The star's location in the constellation Vulpecula, the Little Fox, places it in a region of sky visible from Northern Hemisphere observatories during summer months, when the constellation rises high enough for good observations. The star is not visible to the naked eye, too faint to pick out without optical aid, but easily observable with small telescopes and well within reach of professional instrumentation for detailed study. The distance of 64.5 light-years makes this one of the closer hot Jupiter systems known, bringing the planet within range of more detailed study than would be possible for similar worlds orbiting more distant stars. Light-years measure the distance light travels in 1 year, so the light we observe from this system left 64.5 years ago by our clocks, though this delay has no practical effect on our observations, since conditions remain stable over such timescales. The discovery announcement in October 2005 marked the addition of another hot Jupiter to the growing census of such worlds, but few could have anticipated how thoroughly this particular planet would be studied in the years to follow. The favorable observing geometry, the bright host star, and the intrinsic interest of the extreme atmospheric conditions combined to make this world a prime target for every new observational technique and instrument that came along. The timing of discovery placed this planet in the early phase of serious exoplanet atmospheric characterization, when astronomers were just beginning to develop the techniques that would eventually reveal atmospheric composition, temperature structure, wind speeds, and even color for worlds orbiting other stars. This planet became a testbed for many of these techniques, its favorable properties allowing demonstrations of what might be possible for studying exoplanet atmospheres. The announcement built on decades of prior work establishing that planets orbiting other stars exist at all, a question that had been debated throughout human history, but not settled until the first confirmed detections in the 1990s. Each new discovery in the early 2000s added to the growing conviction that planets are common throughout the galaxy, with huge implications for questions about life and cosmic abundance. The discovery paper documented the basic parameters that observations could reveal: the orbital period of about 2.2 days, the size roughly that of Jupiter, the mass slightly larger than Jupiter, the transit depth of about 2.5%, indicating how much starlight the planet blocked during each crossing. These fundamental measurements established the foundation on which all subsequent study would build. The naming convention that produced the designation HD 189733b follows standard astronomical practice, with HD referring to the Henry Draper catalogue of stars, the number identifying the specific star in that catalogue, and the lowercase b indicating the first planet discovered orbiting that star. The name lacks poetry, but provides precise identification, allowing any astronomer to know exactly which object is under discussion. Subsequent years brought intensive observation campaigns using telescopes on the ground and in space, gradually building the detailed picture of atmospheric conditions that we have explored throughout our journey tonight. The discovery was the beginning, the first step in a process of characterization that continues to the present day as new instruments and techniques reveal ever more detail about this distant world. The detection of glass rain and supersonic winds and blue coloration all came later, built upon the foundation of the initial discovery that told us merely that a large planet orbited close to this star. The story of this world's characterization represents the story of exoplanet science itself, growing from simple detection toward ever more detailed understanding of what conditions prevail on worlds we will never visit directly. The techniques that allow astronomers to study the atmosphere of a planet 64 light-years away represent some of the most impressive achievements in modern observational astronomy. Extracting information from light that has traveled for decades across interstellar space to reach telescopes waiting to decode its messages. We cannot see this planet as a resolved image, just a point of light blended with its much brighter star. Yet we know details about its atmospheric composition, temperature, winds, and color through clever analysis of spectral information. Transmission spectroscopy works by observing the star while the planet is transiting. When starlight must pass through the thin ring of atmosphere visible around the planet's dark disk before reaching our telescopes. As this light passes through the atmosphere, certain wavelengths are absorbed by specific atoms and molecules, while other wavelengths pass through relatively unaffected. The pattern of absorption depends on what substances are present in the atmosphere. Different elements and molecules absorb light at characteristic wavelengths, creating fingerprints that allow identification even across interstellar distances. Sodium absorbs at specific orange wavelengths. Water absorbs across broad infrared regions, and other substances show their own distinctive patterns. By carefully measuring the starlight during transit and comparing it to starlight when no transit is occurring, astronomers can detect the subtle signatures of atmospheric absorption. The detection of sodium in this planet's atmosphere through transmission spectroscopy represented one of the early triumphs of exoplanet atmospheric characterization, demonstrating that specific elemental abundances could be determined for worlds far beyond our solar system. The sodium was detected at high altitudes, indicating that the atmosphere extends far above where most of the atmospheric mass resides, reaching up to where sodium atoms can absorb starlight during transits. Emission spectroscopy offers a complementary view by observing the planet's own thermal radiation rather than starlight filtered through the atmosphere. Hot planets glow with their own light, emitting infrared radiation characteristic of their temperature, and this emission can be measured when the planet passes behind the star during secondary eclipse. By comparing the total light when the planet is visible to the light when only the star is visible, the planet's contribution can be isolated. The thermal emission reveals temperature directly, since the spectrum of a glowing object depends on how hot it is, with hotter objects emitting more light at shorter wavelengths. The extremely high temperatures of this planet's day side produce thermal emission detectable by infrared space telescopes, allowing the temperature to be measured directly rather than just modeled. The approximately 1200 degrees Celsius dayside temperature comes from such measurements. Phase curve observations track how the total light from the system changes throughout the planet's orbit, as different portions of the planet's surface or atmosphere face toward Earth at different orbital phases. When the hot day side faces Earth most directly, the system appears slightly brighter in infrared than when the cooler night side faces us. These variations reveal how heat is distributed across the planet and how efficiently the atmosphere transports energy. The wind speed measurement came from detecting Doppler shifts in atmospheric spectral lines, a technique that reveals motion directly through the change in wavelength that moving sources produce. Gas moving toward us shifts light slightly bluer, while gas moving away shifts light slightly redder. By measuring these shifts for atmospheric features during transit, when some atmospheric gas approaches us while other gas recedes, wind speeds can be determined. The blue color measurement required an entirely different approach, comparing reflected starlight at different orbital phases to determine how much light of each color the planet reflects versus absorbs. This measurement used the Hubble Space Telescope's ability to observe at multiple visible wavelengths simultaneously, isolating the planet's contribution through the secondary eclipse technique applied to visible rather than infrared light. Water vapor was detected through its characteristic infrared absorption features, appearing in both transmission spectra, taken during transit, and emission spectra, taken during secondary eclipse. The presence of water, even at these extreme temperatures, tells us something about the atmospheric chemistry, since water molecules persist at concentrations measurable from interstellar distances, despite conditions that would seem hostile to their survival. Each technique has strengths and limitations, probing different portions of the atmosphere at different wavelengths and revealing different aspects of atmospheric structure and composition. The combination of multiple techniques applied over many years has built the comprehensive picture we now have of conditions on this world, a picture no single method could have provided alone. The telescopes involved include both space-based observatories like Hubble and Spitzer, and ground-based facilities using adaptive optics and high-resolution spectrographs to achieve the precision necessary for these delicate measurements. Each facility contributes particular capabilities, and the coordination of observations across many instruments has been essential to progress. The James Webb Space Telescope has added its capabilities to the study of this planet, offering infrared sensitivity superior to any previous instrument and enabling new discoveries about atmospheric composition and structure. Observations with Webb continue to add detail to the picture built over nearly 2 decades of study, demonstrating that there is still more to learn about even well-characterized worlds. The methodology developed for studying this planet applies broadly to exoplanet characterization throughout the galaxy, with techniques refined here being applied to newly discovered worlds that may be harder to observe but benefit from the experience gained on easier targets. This world has served as a training ground for exoplanet atmospheric science. The resemblance to Jupiter goes beyond coincidence of name, since this world shares the same basic nature as our solar system's largest planet, a giant ball of mostly hydrogen and helium gas, without solid surface or ground. Yet the conditions could hardly be more different. The comparison between these two gas giants reveals how profoundly environment shapes planetary character, taking similar raw materials and producing vastly different atmospheric conditions through the simple difference of orbital position. Jupiter orbits our Sun at an average distance of about 778 million kilometers, roughly 5 astronomical units, from the solar source of heat and light. This distant orbit places Jupiter in the cold outer regions of our solar system, where temperatures at the cloud tops drop to approximately minus 150 degrees Celsius, cold enough to freeze ammonia into the cloud crystals that give Jupiter its distinctive banded appearance. The cold preserves Jupiter's original rotational spin. This world orbits its star at only 4.6 million kilometers, about 169 times closer than Jupiter orbits our Sun, and experiences correspondingly more intense radiation, despite orbiting a slightly dimmer star. The 1200-degree temperatures on the day side of this world compare to the minus 150 degrees of Jupiter's cloud tops, a difference of over 1300 degrees arising purely from the different orbital positions these two similar objects occupy. Both planets have masses comparable to Jupiter. Both have radii slightly larger than Jupiter, and both are composed primarily of hydrogen and helium, with smaller amounts of heavier elements mixed into their atmospheres. The raw materials are similar, because both formed from the gas present in their respective protoplanetary disks, dominated by hydrogen as the most abundant element in the universe. The fundamental chemistry is shared. Jupiter's atmosphere contains clouds of ammonia ice at the top, water ice below, and complex organic compounds that produce the brownish and reddish colors visible in telescopic images and spacecraft photographs. The banding pattern results from atmospheric circulation driven by Jupiter's rapid rotation, with alternating zones of rising and sinking air creating the striped appearance that has fascinated observers for centuries. The clouds are cold and varied. This world has silicate particles instead of ammonia clouds, glass rain instead of water ice, precipitation, and temperatures too hot for any of the condensates that characterize Jupiter's atmospheric chemistry to survive in solid or liquid form. The circulation pattern is driven by the day-night temperature difference rather than by rotational effects, creating a fundamentally different atmospheric dynamic, despite the similar underlying planetary structure. Jupiter rotates once every 10 hours, spinning rapidly enough to bulge noticeably at the equator, and to drive the strong Coriolis effects that organize atmospheric circulation into bands parallel to the equator. This world rotates once every 2.2 days, synchronized to its orbital period by tidal locking, slowly enough that rotational effects play much smaller roles in atmospheric dynamics than they do on Jupiter. The moons of Jupiter number over 90 at current count, a miniature solar system of satellites, ranging from tiny rocks to worlds larger than Mercury, some with subsurface oceans and active volcanism and other features that make them fascinating objects of study in their own right. This world almost certainly has no moons, since the close orbit to the star leaves no stable region where a moon could exist for astronomical timescales. Hot Jupiters, like this world, were not predicted to exist before they were discovered. Since planetary formation theory expected giant planets to form only in the cold outer regions of planetary systems, where ices could supplement rock in building the cores that attract hydrogen envelopes. The discovery of giant planets orbiting extremely close to their stars forced revision of these theories. The current understanding is that hot Jupiters did form in the outer regions of their systems, as theory originally expected, but then migrated inward through gravitational interactions with the disk material or with other bodies in the system. This migration process carried them from cold outer orbits to the scorching inner positions where we observe them today, transforming their atmospheres in the process. The migration that brought this planet to its current orbit probably occurred early in the system's history, when disk material was still present to drive orbital evolution, or when other giant planets existed to scatter this one inward through gravitational encounters. The details remain uncertain, but the basic picture of inward migration is widely accepted as the explanation for how hot Jupiters reach their surprising positions. Jupiter will remain cold and banded and rapidly rotating for billions of years to come, maintained in its distant orbit by the gravitational architecture of our solar system that has persisted since early formation epochs. This world will remain hot and wind-blown and tidally locked for similarly long timescales, its conditions as permanent as its orbit around the star it almost touches. The comparison illuminates how diverse planetary outcomes can be, even starting from similar initial conditions, how the accidents of orbital history can transform similar raw materials into utterly different end states. Jupiter and this world share a family resemblance, visible in mass and composition. Yet their atmospheric experiences could hardly be more alien to each other. The atmosphere extends deep below the regions we can observe directly, layers piling upon layers, with increasing temperature and pressure toward a depth where conditions become too extreme to characterize with confidence. The upper atmosphere where glass rain forms and where our observations probe represents only the accessible outer skin of an atmospheric column that continues downward without clear boundary or ending, a gas giant lacking any surface where the descent could stop. The composition of the atmosphere is dominated by hydrogen and helium, the same elements that dominate Jupiter and the Sun, and indeed most of the matter in the universe, light elements formed in the Big Bang rather than in stars. These simple atoms form the bulk of the planetary mass, providing the medium through which trace species like silicates and water and sodium create the observable phenomena we have discussed. The hydrogen and helium themselves contribute little to spectral observations. Water vapor has been detected despite the extreme temperatures, surviving in molecular form in the upper atmospheric regions where observations probe most effectively. The presence of water tells us that oxygen is available and that conditions permit at least some molecules to persist despite the thermal energy that might be expected to break them apart. Water is a surprisingly robust molecule under many conditions. Sodium was among the first species detected through transmission spectroscopy, its distinctive orange absorption lines appearing clearly when starlight passed through the atmospheric limb during transits. The sodium exists at high altitudes, high enough to intercept starlight around the limb of the planet, indicating that the atmosphere extends far above where most mass resides. The detection established that atmospheric characterization of exoplanets was possible. Potassium has also been detected, another alkali metal with characteristic absorption features that appear in transmission spectra, adding to the inventory of identified atmospheric constituents. The alkali metals are expected theoretically in hot giant atmospheres and have now been confirmed observationally for this world and several others. Theory and observation align. The silicates that form the glass rain have been identified through their effects on the spectrum, absorbing light across broad wavelength regions and contributing to the scattering that produces the blue color observed in reflected light. These materials exist in both vapor form at deeper, hotter levels and as condensed particles at higher, cooler altitudes. The vertical distribution creates the rain phenomenon. Carbon monoxide is likely present based on theoretical models of atmospheric chemistry at these temperatures, though direct detection is challenging, and not all predicted species have been definitively confirmed through observation. The chemistry of a hot hydrogen-dominated atmosphere includes many species not found in cooler planetary atmospheres, molecules that would not survive at Earth temperatures but persist under these conditions. The atmospheric layers differ in temperature and composition, with different species condensing or dissociating at different altitudes, depending on local conditions. The upper atmosphere, where transmission observations probe, differs from the deeper atmosphere sampled by emission observations, and combining different techniques reveals how properties vary with height. The three-dimensional structure is complex. The pressure increases with depth, as in any atmosphere, and this pressure affects both chemistry and phase behavior of atmospheric constituents. Higher pressure allows materials to remain gaseous at temperatures where they would condense at lower pressure, shifting the altitudes where clouds and precipitation can form. The vertical structure reflects the combined effects of temperature and pressure. The atmospheric escape that may be occurring in the uppermost layers, where intense stellar radiation heats gas to the point where atoms can achieve escape velocity, represents a slow leakage of atmospheric mass into space. This process has been detected for some hot Jupiters, and likely operates here as well, though the planet is massive enough that significant atmospheric loss over the age of the system is unlikely. The deeper atmosphere remains mostly unknown, hidden from observational access by the overlying layers that block or reprocess any light that might carry information from great depths. What happens below the observable skin is inferred from models and theory rather than measured directly, a limitation that applies to gas giants, generally including Jupiter itself. The layered structure creates the conditions for the phenomena we have observed: the silicate condensation in upper cooler layers, the temperature structure that drives atmospheric circulation, the chemical complexity that produces measurable spectral signatures. The atmosphere is a system, with its parts connected through circulation and chemistry, in ways that observations are gradually revealing. The study of this world continues with new telescopes and new techniques adding detail to the picture built over nearly 2 decades of intensive observation since its discovery in 2005. The James Webb Space Telescope has observed this planet, bringing capabilities in infrared spectroscopy that exceed any previous instrument and promising new discoveries about atmospheric composition and structure that will add to our understanding. Webb's observations can probe atmospheric regions and detect chemical species that were beyond the reach of earlier instruments, extending the wavelength coverage and improving the sensitivity of atmospheric characterization. The results from Webb observations continue to be analyzed and published, each new study adding information that refines the picture or reveals previously unknown aspects of this complex atmospheric system. Questions remain about the exact composition of the silicate clouds, whether they are primarily silicon dioxide or other silicate minerals, how their properties vary with altitude and location, how they form and dissipate over time. These details affect the atmospheric dynamics and the optical properties that produce the observed blue color, making them important for comprehensive understanding. The three-dimensional structure of the atmosphere, how conditions vary not just with altitude, but across the globe, from dayside to nightside, and from equator to pole, remains incompletely mapped despite the extensive observations accumulated over the years. Future observations with higher resolution and different techniques may reveal asymmetries and variations that current data cannot distinguish clearly. Atmospheric variability over time is another area of uncertainty, since most observations sample snapshots rather than continuous monitoring, leaving open the question of whether weather patterns change over time or remain static indefinitely. Some observations have hinted at variability, but confirming and characterizing any changes requires repeated observation campaigns spanning significant time intervals. The wind speed measurements, while establishing the general magnitude of atmospheric motion, have considerable uncertainty in their exact values, and different observational approaches have yielded somewhat different results. Refining these measurements and understanding the discrepancies will require continued observation and improved analytical techniques. Comparison with other hot Jupiters helps place this world in context, showing which properties are typical of the class and which are distinctive to this particular planet. Each hot Jupiter has its own characteristics, reflecting its particular star, orbit, composition, and history. And understanding the diversity of the class requires studying multiple examples in detail. This world serves as a benchmark for atmospheric models, providing observational constraints that theoretical predictions must match to be considered successful. Models that reproduce the observed properties of this atmosphere can be applied with greater confidence to less well-studied worlds, where observational data is more limited. The techniques developed and refined through study of this planet continue to be applied to newly discovered worlds, including potentially habitable planets around other stars that attract intense interest but present much greater observational challenges. The lessons learned from studying this hostile but accessible world inform the study of worlds more likely to be hospitable. The field of exoplanet atmospheric characterization continues to advance rapidly. With new missions planned and new techniques under development that promise to reveal ever more about conditions on worlds beyond our solar system. This planet will likely remain a reference target as new capabilities come online, its well-characterized properties providing a standard against which to test new instruments and methods. The ongoing discovery extends across the entire field of exoplanet science, with each new observation adding to human knowledge about the diversity of worlds throughout the galaxy. This particular planet has contributed enormously to that knowledge, serving as a laboratory for atmospheric physics under conditions impossible to replicate on Earth or anywhere in our solar system. The planet continues its orbit tonight, as it has for billions of years, circling its star in just over 2 Earth days, completing circuit after circuit while the glass rain falls sideways through the screaming winds, and the blue atmosphere glows with heat absorbed from the ever-present star, dominating its sky. The world exists whether we observe it or not, persisting in its extreme conditions, independent of human attention or awareness. 64 light-years separates this world from ours, a distance that light crosses in 64 years, meaning the starlight we observe tonight left that star when people now elderly were young, traveling all that time through interstellar space to finally reach telescopes waiting to capture it. The separation is vast by everyday standards, yet modest by galactic standards. Close enough that detailed study is possible, far enough that no visit is conceivable. The planet will continue circling its star for billions of years to come. The conditions we have explored persisting indefinitely, as long as the star continues shining with similar intensity and the orbital configuration remains unchanged. The glass will continue raining, the winds will continue blowing, the blue color will continue characterizing the reflected light, all the phenomena simply continuing because the physics demands it. Nothing about this world is hospitable to life as we know it. The temperature's too extreme, the chemistry too harsh, the environment too alien for any biology we could imagine surviving there. This is not a world where anyone will ever walk or breathe, or observe the strange weather from within. It is a world we know only through light and inference, and the patient work of astronomers building understanding from distant observation. The existence of such a world expands our sense of what planets can be, how strange the conditions elsewhere in the universe compared to the relatively mild environment we inhabit here on Earth. Before worlds like this were discovered, our imagination of planetary diversity was constrained by the examples in our own solar system. Now we know that far stranger things exist. The thousands of exoplanets known today include many hot Jupiters and many other extreme worlds, each with its own characteristics, shaped by its particular circumstances. This planet is one among thousands, yet it is also unique. The specific combination of conditions found here occurring in this exact form only at this particular location around this particular star. The light from this star that reaches us tonight has been traveling for decades, carrying encoded information about conditions that prevailed when it departed, information that patient analysis can extract and interpret. The star appears as a faint orange point in the constellation Vulpecula, if you know where to look. Unremarkable to casual observation, harboring its extreme world invisibly. The blue color, confirmed by careful measurement, makes this planet superficially similar to our own blue world, while being utterly different in every other way. The coincidence of color connects two planets across 64 light-years, while emphasizing how different the causes of similar appearances can be. Earth is blue because of water and air. This world is blue because of glass. The extreme winds carry heat from day to night, endlessly. A circulation pattern that has operated since the planet reached its current orbit and will continue operating for as long as the tidal locking and stellar heating persist. The atmosphere churns, but the pattern remains constant. Endless motion in an unchanging arrangement. Dynamic stability on cosmic timescales. The glass rain falls sideways through these winds. Particles condensing and falling and evaporating and condensing again in an endless cycle. Weather unlike any weather on Earth, yet operating through the same basic physics of condensation and precipitation that produces familiar rain here. The physics is universal, even when the materials and conditions are not. Looking up at the night sky from Earth, somewhere in the direction of the Little Fox constellation, this strange world orbits its orange star, real and present, and doing everything our observations have revealed it does. The planet exists independent of our knowledge, but our knowledge allows us to understand something about what existence there entails. The conditions that persist in that alien sky. The world continues tonight and will continue through the night, and will continue for billions of years after this night has ended. And we who contemplate it have gone. The glass rain keeps falling, carried sideways by winds beyond Earth experience, through an atmosphere colored blue, by particles that sparkle faintly in the light of a star, too close for comfort. On a world 64 light-years away that we have slowly come to understand, through the patient work of science, reaching across the distances that separate us from all the strange worlds scattered throughout the galaxy.